Okay, we're going to start week 7. Week 7 basically is two things. They're called related rates problems. And then the other thing, which is really relatively small, is called linearization. Related rates problems usually are one of the tougher things in Calc 1 because they're word problems. So each problem, you will see some type of wording that leads you to a formula. Okay, and I cut the amount of different types of problems down. One thing that's really popular is the Pythagorean theorem is really popular. Area of a circle is really popular for a formula. Sometimes sine, cosine, and tangent formulas are really popular. This first one says something about a conical tank. And it's going to be 3 dimensions because there's water in it. So conical means cone. So anything that is 3 dimensions and it mentions in this case a cone is going to be a volume formula. So volume of a cone is 1/3 pi r squared h. So now this is the hard part about the problem is this problem is finding out like what the different things are in the problem. So all of these problems, things are going to be changing. In this case, water's running into the tank. So this is, a conical tank. It looks like this. And as water is going into this tank, you can see that the height is getting bigger. The radius is getting bigger, as volume of water goes in this tank. So what we want to do is we want to find out how fast the water is rising. So whenever it says something about like how fast, that's always a rate. So after you kind of draw a picture, after you get a little formula together, the second step you can see is we're going to differentiate this. We're going to take this derivative, but we've always been taking the derivative, with respect to x, because the derivative of x is 1. Now we're going to be taking the derivative with respect to time. So the derivative of v is dv dt. That's the derivative of v, dv dt. So instead of saying v prime, say dv dt. Now what this dv dt is, it's the rate that the volume is changing of water. So we're going to put the 9 in a minute in there, okay? Equals. Now you can see over here there's 2 variables. Usually when there's 3 variables in total, 2 on one side, usually what you want to do is you want to get rid of one of the variables because the derivative is much easier. So actually they give you a formula up above here. They tell you something about the height and the radius of this cone, all right? So what you can do is you can make a little formula that the height is always twice the radius because the height is 10 and the radius is 5. So that would be if it was all the way filled up. So now what you can do is you can eliminate one of those variables. Well, you might say, well, how do I know if I'm going to eliminate the r's or the h's? Well, what you have to do is you have to read the problem and see what they tell you. If they tell you something about the height, that means you want to keep the h's. If they tell you something about the radius, that means you want to keep the r's. So this one says, how fast is the water level rising? Well, that's something with the height. And then it says when the water is 6 feet deep, that actually is the height. Okay, so we want to keep the h there. So what you want to do then is you want to solve for r real fast. So it's always something very similar. Okay, so now this formula, before we take the derivative, we're going to have to change it a little bit. Okay, and write the volume here, 1/3 pi. So we want to get rid of the r. So we have h over 2 the quantity squared times h. So the volume, when you're all done, is 1/12. 2 squared is 4 times 3 is 12. Pi. And then h cubed. Like that. So now we're ready to take the derivative. So once again, the derivative of v is dv dt. When you take the derivative of this, 3 times 1/12, so we'll just write 3/12 there. Pi comes along because it's a number. H goes to the second power. You drop it by 1, and then you take the derivative of h, dh dt. So this is like this y prime that we did before, okay? So now after you take the derivative, you just plug in numbers. So dv dt is how the volume is changing. Right here, this number, this is how the volume is changing. Feet cubed is a volume measurement per unit of time, per minute. So that tells you something about how the volume is changing. So we're going to put 9 in for that. This is 1/4. We'll just simplify pi. So now it says we want to figure out how the height is changing. How fast is the water level rising? So that's a rate on how the height is changing. So we want to find dh dt. This is how fast the height is changing. And then exactly at the minute that the height is, let's see, I think it says 6. Yeah, when it's 6 feet deep, right? So 6 squared. When the height is exactly 6, we want to figure out at what rate the height is changing. So then what you do is you just simplify. So this is 36 pi over 4, and then dh dt is the variable. So that's the rate in which the height is changing. All right. So then a lot of these you really don't need a calculator for. So 9 equals 9 pi, and then dh dt. 9's cancel, and then dh dt. So dh dt is 1 over pi. So this is the rate that the height is changing. So pi is about 3. So this is about 1/3. And then you have to go back and look at the units. So the height, I believe, is measured in feet, and then the time is per minute. Okay. So this unit is 1 over pi feet per minute. This is the rate the height is changing. This is your answer. Okay. So what we're going to do is we're going to do some other ones. We're not going to go in order. We're going to do some of the easier ones first. So that one was a little bit harder because you had to get rid of one of the variables because there was 3 of them. So now if you go down to number 4, this is a little bit easier because you have this pebble, and this pebble is dropped in a pond. And then you can see when a pebble's dropped in a pond, these concentric circles keep going out. So then what happens is you can see the area of our circle gets bigger. The radius of our circle gets bigger. So this says something about area. So area of a circle is pi r squared. So now this one only has 2 variables. It has an a and an r. So you're good to go. You don't have to get rid of one of the variables or anything like that. So the derivative of a is dA dt. This is how the area is changing. Equals 2 times pi, 2 pi, r goes to the first power, and then the derivative of r is dr dt. Everything is with respect to time. So what dr dt means, that's how fast the radius is changing. That's how fast it's getting bigger. So now let's see what they give us in the problem. It says a pebble is dropped into a pond, causing ripples to form concentric circles, which we have. The radius r is increasing at a rate of 1 foot per second. All right, so they give us how fast the radius is changing, 1 foot per second. That's 1 right there. That's dr dt. When the radius is 4 feet, all right, so they give us radius at 4 feet exactly, how does the area changing? We want to figure out how the area of our circle is changing. When the radius is exactly 4 feet, if the radius is changing at 1 foot per second. So you just multiply all these together. So this one is really easy. So the rate the area is changing is 8 pi. Area is always measured in square units. So this would be, in this case, feet squared per, there's your divided by sign, and then the time in the problem is seconds. So it's just an S. So every second that goes by at that particular moment, the area is getting bigger by 8 pi. Okay, so that's one that was the area formula of a circle. The next one, this is a volume problem. Do you see it says cubic feet per minute? Anytime it says something about cubic, that's a volume. So air is being pumped into a balloon. So the balloon, here's this tube and it's pumping air into a balloon. The balloon is a circle. Okay, it's a sphere, actually, a sphere. So volume of a sphere, if you didn't know, is 4/3 pi r cubed. Okay, that's the volume of a sphere. So we want to figure out the rate that the radius is changing. So this one has two variables like the other one. So dv dt is the derivative of v. Here we go. 3 times 4/3 is 4. Pi comes along. R goes to the second power. And then the derivative of r is dr dt. So now this is how the volume is changing. They give us that at 4.5 cubic feet per minute. So this is 4.5, 4 pi. Now let's see. It says find the rate of change of the radius. So we want to find dr dt, how the radius is changing when the radius is exactly 2 feet, 2 squared. Okay? So now to get dr dt alone, you just divide everything over there. Over here, you get 16 pi. So we'll kind of write it out. So 4.5 equals 16 pi dr dt. So this one you get 4.5 over 16 pi. That's dr dt. So the radius is a single measurement. So that's feet, inches, miles, whatever. Let's see what it is. So looks like feet. So the unit is feet per. And then time is measured either usually in seconds or minutes or something like that. So you go back up and it's measured in minutes. So MIN. Okay. So that's a volume problem using a sphere, which is very common. This one over here, number 6, we'll do that one there. This is dx dt is how the x's are changing. And then we want to find dy dt, how the y's are changing, exactly when x is 3 and y is -4. So this equation up here, you're used to taking the derivative with respect to x. This one, we're going to take the derivative with respect to time. Okay, so this one's a little different. So the derivative of x squared is 2x, and then the derivative of x is not 1. The derivative of x is dx dt. So that's where it's a little bit different, this one. The next one, the derivative of y squared is 2y, and then the derivative of y is dy dt. And we're used to putting y prime there, but that's when we took it with respect to x. So now we're taking it with respect to time. And then the derivative of 25 is 0. So what you can do is you can cancel all the 2's out. You divide everything by 2. So now let's see what they give us. They give us dx dt is -2. X is 3. Just plug it in. We want to find dy dt when y is -4. So we want to find out how y is changing when x is 3 and y is -4. So you just manipulate those variables. So you get -4 dy dt, and then you move this guy over to the other side. So this is -6. So over there, it's going to be +6. So dy dt is going to be 6 over -4, which is -3/2. There are no units here, so that's all you can do is -3/2 there. Okay. All right. Let's do a couple more and then we'll end the video. All right, this one. Okay, let's do a ladder problem. A ladder problem is a good problem here, number 8. All right, number 8, it says a 25-foot ladder is leaning against a house. So here you have your house, right? And here's the ladder leaning up against the house. the ladder is always 25 feet. The ladder never ever changes. So you can see the ladder makes a right angle with the building, okay, with the house. So you can put house here. One. So now, what's going to happen in these ladder problems is the ladder's going to start sliding down the house. So we'll call this guy Y here, and we'll call this X. So as the ladder slides down, Y is going to get smaller and X is going to get bigger because the bottom of the ladder is going to, it's going to go this way. Okay? So now what relationship always holds is the Pythagorean theorem until it gets to the very bottom. The Pythagorean theorem always holds in this case for this particular. Ladder problems are usually an angle when you have a trig function, or it might be a ladder problem like that. So now it has to give you some information, only two variables, so you can take the derivative. So the derivative is 2x dx dt. This is the rate x is changing. And then 2y dy dt. This is the rate y is changing. And then the derivative of 25 squared, remember that's a number, is 0. You can get rid of the 2's like we did before in that last problem. Zero. So now let's see what they give us. A 25-foot ladder is leaning against a house and the base starts to slide away, which is what we said. By the time the base is 7 feet from the house, okay? So now it told us something about X. It's 7 feet away from the house. It's moving away at a rate of 2 feet per second. So X is moving at 2 feet per second. So every second that goes out, X is moving 2 feet to the right. How fast is the top of the ladder sliding down? That's how fast Y is changing. All right. What is the rate the angle is changing? So we'll do that in a minute, but this is the first thing. So now what we don't know is, we don't know actually two things. How fast is the top of the ladder sliding down? Well, that's how Y is changing. We don't know what Y is, but what we can do is we can actually go back here and put in 7 for X and figure out, what Y is going to be by doing the Pythagorean theorem. So when you do the Pythagorean theorem, this is one of these triples that you might have remembered from geometry. So in this case, Y is going to be 24. So you just plug that in there. All right. So now you get 14, and you're going to move that to the other side. So that'll be negative. So the rate that Y is changing is negative 14 over 24. Which is 7 over 12, negative. And then this is feet per and feet per second for that one. Okay, second. All right, so that's how you find how fast Y is changing. So now the angle's a little different for this one. You want to figure out something about the angle. You can actually do this a couple different ways. The angle, you still have the same triangle, all right? That's no different. So you're not going to put an angle there, okay? I probably would keep Y there, and then this 25 is going to be there. You can keep the X or the Y. It doesn't really matter. So when you set this one up, and this one will require a calculator, the sine of theta is equal to Y over 25, which is 1 over 25y, like that. So when you take the derivative of sine is cosine. Angle stays the same. So here's something new. The derivative of theta is d theta dt. The derivative of 1/25th y is 1/25th dy dt. All right? So now, what we have to do is we have to find the angle, okay? The angle, we go back to the original formula. We know when x is 7, y is going to be 25. So what we have to do to figure out the angle, and then we can plug the angle in, is the sine of the angle is equal to y we know is 24 over 25. So this is where you're going to have a calculator on this next exam that you might come into a problem like this where you have to figure out the angle. Okay, so let me get my calculator. It doesn't matter whether you use degrees or radians, it's the same thing. So you hit second function sine, and then you hit 24 divided by 25. And you get about 74 degrees. So we'll just say it's 74 degrees. Whoops, degrees. And you can round to get your answer a little bit closer to mine, okay? So now you're ready to roll. The cosine of 74 degrees, we want to figure out how the angle is changing. So that's the theta dt, that's the rate the angle is changing. 1/25, and then we know dy dt, we just figured that out, was negative, what was it, negative 7 over 12. Yeah, from above, yep, negative 7 over 12. Okay? All right, so now we're just ready to punch everything in our calculator. So we punch all this in our calculator, so you hit 1 divided by 25, and then you multiply it by negative 7 divided by 12, hit equals, and then you divide that by the cosine of 74, hit equals. So that'll give you how much your angle is changing. So 0.08 negative. And the unit for that is always radians per whatever unit of time that is. In this case, let's see, what's the unit of time? It's seconds. So this problem actually had two different problems in it. It had an angle that was changing as the ladder was falling down, and you can see the angle, we got a negative measurement here, so the rate of the angle is getting smaller, which is true as the ladder falls down, okay? All right, let's see if we can do one more. This one is a little different. It's kind of like what we did a little bit just a minute ago, number 7. It says a girl flies a kite of 300 feet. The kite always stays at 300 feet. All right, so there's a person down here probably holding the kite string. So here's the kite. So you can see there's going to be a right angle here because this is kind of a made-up problem. The kite is always moving in that direction, okay? And the height is always 300 feet. So that's never a variable because that's always 300 feet, okay? The wind carries the kite horizontally away from her at a rate of 25 feet per second, all right? So this x value is going to get bigger as the kite goes out, all right? It says, how fast must she let out string when the kite is 400 feet away from her, okay? So how fast must she let out string? So here's the string on the kite. So when this kite is moving out this way, Pythagorean theorem always holds. X squared plus 300 squared equals z squared. So we want to figure out the rate that the string is going to be let out, which is dz dt. So when you take the derivative, you get that. The derivative of a number is 0. 2z dz dt. All right, 2's can cancel. So now let's see what they give us. The wind carries the kite horizontally away from her at a rate of 25 feet per second. This is the rate x is changing. It's feet per second. How fast must she let out string? That's dz dt. That's our variable. That's what we're figuring out. All right, so now we need to know x and z. So now let's see what else they give us. How fast must she let out string when the kite is 400 feet away from her? So that's what x is going to be. So what you do is you plug 400 back in for x, and then you can find z. So 400 is x, which goes here. So this is our, if you remember this one, this is our 3, 4, 5. It's a Pythagorean triple. I like to use Pythagorean triples a lot. So z is 500. It just makes the math a little easier, which is 500. So then what you do is you take 400 times 25 and you move that over. Oh no, you don't have to move that over. You just take 400 times 25 and you get 10,000. And the 500 is over there with the variables. So you just divide by 500 and you get 20. So 20 is dz dt. This is the rate that she's letting out string. And it's probably feet per second or something like that. Yes, it is feet per second. Yeah, so this is feet per second. So every second that goes by, as the kite's moving out, she's got to let out 20 feet per second. All right, we're going to stop the video there. And then these were, I know they're probably not basic to you, but they're kind of more basic problems. So now we'll do ones that are a little more difficult in the second video concerning these.